This is the supplementary video for lecture 20. We finished 5 problems in class but leaving 3 unsolved. And let me just explain the solutions in this supplementary video. So we will start from the last problem. So we wish to find the equation of the line through the point 3,5 that cuts off the least area from the first quadrant. So to understand the situation, let's start by drawing the coordinate axis. Then plot the point 3,5. All right, so this is the point. Okay, let's say we have got a line of negative slope passing through 3,5. Then you can see that this line will cut out the first quadrant this much. So we will wish to minimize this area. On the other hand, what happens if we have got a line of positive slope? Well, you see that in this case, first quadrant is cut into 2 parts, but each part has infinite area. So no matter which part is considered to be cut off, we will not bother to consider this situation. All right, so then let's simply focus on the case when we have got a negative slope. And let's introduce the notation K for the slope of the line. So from the previous analysis, we are focusing on the case when the slope is negative. Then on the other hand, the line equation would then be y minus 5 equals to k times x minus 3. All right, so this will be the equation for the line. Okay, so let's actually draw such a line on the plane. So let's say that this will be the line passing through the point 3,5. And now, well, to get the area of this part, well, we need to understand the x-intercept and the y-intercept. So x equals to 0 implies that y minus 5 equals to k times minus 3. So this will imply that y equals to minus 3k plus 5. Okay, so this is basically the coordinate of this point. We know that this one is minus 3k plus 5. On the other hand, to get the x-intercept, we simply set y equals to 0. So this will tell me that minus 5 equals to k times x minus 3. So divide both sides by k because we assume the k is non-zero. So that way we get x equals to 3 plus 5 over k. Actually minus, not plus. So this 3 minus 5 over k will then be the x-intercept. As you can see that if we let A be the area of the part cut off by the line in the first quadrant, so then we see from the picture that this area is going to be 1/2 times the x-intercept times the y-intercept. I don't think it's necessary to multiply this guy out, although it might be simplifying the computation a little bit. Okay, so let's actually still multiply out. So, so you could actually get minus 1/2 times. So I don't think it's necessary to multiply this guy out, but it seems that this is still going to make it simpler. So you could either try to use the product rule or multiply everything out and directly use power rules to do the term-by-term differentiation. And let's actually multiply it out. So that's how we will get 1/2 times minus 9k plus 15. So that will be the positive 3 times the second guy. Then I will just multiply minus 5 over k with the second guy. That will simply be plus 15 and then minus 25 divided by k. Yep, so that's why we get. So the answer for this will be 1/2 times minus 9k plus 30 and then minus 25 divided by k. Okay, so we can compute the derivative of a versus k, which will simply be 1/2 times minus 9 plus 0 and then plus 25 divided by k squared. Okay, so we can simplify this guy as 1/2 times minus 9k squared plus 25 divided by k squared. Okay, so because we assume that k is negative, so this guy exists everywhere in the domain, so I don't need to worry about the case when the denominator equals to 0. So then dA over dk equals to 0 implies that 9k squared equals to 25. So that basically tells me that k is going to be negative root of 25 divided by 9. And I'm not worrying about the negative positive roots for this guy because we assume the k is negative. So that's all I need, and the answer will be minus 5/3. Okay, so this is the critical number for this guy. Okay, so we could use the first derivative test to see if k equals to minus 5/3 is giving a maximum or minimum. So let's actually draw the domain like this, and then this is going to be my critical number. Okay, so if k is further smaller than minus 5/3, so that means k squared will be actually larger than 25/9. So that basically tells me that 9k squared will be larger than 25, but then 25 minus 9k squared, this will become less than 0. So this says to the left of minus 5/3, so the derivative is negative, and as a result, well, the function is decreasing. Similarly, if you have got k is greater than minus 5/3, so that you will just repeat the process. K squared becomes smaller, 9k squared becomes smaller, and then 25 minus 9k squared becomes larger. So this way you see that the derivative is positive and the function is increasing. So that first derivative test would tell me that A takes absolute minimum at k equals to minus 5/3. All right, so this basically is what you can tell from the first derivative test. Okay, let's see what we are looking for. So we are not looking for the area, we are not looking for the k, we are looking for the equation of the line. So when you formulate your answer, please make sure you answer the correct question so that, well, the answer to this question is the equation of the line minimizing the area is, well, y minus 5 equals to minus 5/3 times x minus 3. So alternatively, you could just use the method that's similar to closed interval method and see the function values. So if k equals to minus 5/3, so you compute that a is going to be equals to 1/2 times minus 9 times minus 5/3 plus 30, and then minus 25 divided by k, that will be 25 divided by minus 5 times 3. Okay, so what do we get from here? So we get 1/2 times 3 times 5 plus 30, and then plus 3 times 5 times 3. Okay, that will be 30 plus 30 divided by 2. The answer will be 30. So this will be the area we get if k equals to minus 5/3. And on the other hand, as k approaches to 0 from the left, so what do we have? Okay, so what we have is actually a is going to be equals to 1/2 times minus 9k. Well, this guy will approach 0, and then plus 30, and then minus 25/k. All right, so this will approach to 1/2 times 0 plus 30, but then, okay, look at what we have over here. So k is going to be negative and very small, so negative k is going to be positive very small, and 25 divided by a positively very small number, that will be infinity. So the answer will be positive infinity. And similarly, if k approaches to minus infinity, so that we see that a is going to be equals to 1/2 times minus 9k plus 30 minus 25 over k. Okay, so, well, the first guy is going to be a negative number times a negatively large number, so that will be positive infinity. So this will be infinity, this will be 30, and this will approach 0, so the answer will be positive infinity. So this guy approaches positive infinity. So this way we see that the area takes absolute minimum at the number 30, so that we can formulate our answer. So then the equation of the line minimizing the area is simply going to be y minus 5 equals to minus 5 over 3 times x minus 3. All right, so that will be the second way of handling this problem. Okay, so let's go over number 16, which I decided to skip because the number is pretty ugly. So let's see what we have. So we need to have got a rectangular storage container, and then it has got open top, and moreover, its volume is fixed. Then we are also assuming that the length of its base is twice the width. And then material for the base costs $10 per square meter, and material for the sides costs $6 per square meter. So we want to find the cost of the material for the cheapest such container. So notice that in this problem, we are looking for the cost. We are not looking for the dimensions anymore. So when you formulate your answer, please make sure you answer the correct question. Now let's draw a container. So it's pretty tricky to draw a nice picture on iPad because I think the tip is a little bit too smooth. It's good for writing, but it's probably not very good for drawing. At least I need to learn how to draw nice pictures on an iPad. Okay, so yeah, this is going to be a rectangular container. All right, and we know that the length is going to twice its width. So if this is going to be the width, then this will be 2a. So let's introduce a notation here. So let a be the width of the base, and let L be the length of the base, and finally let H be the height of the container. So, well, then from our problem statement, we know that the length equals to 2 times the width. And moreover, we know the volume is going to be 10. This means 10 equals to A times L times H. All right. So now because my L equals to 2A, so this way I know that this is going to be A times 2A times H. And this way I express H in terms of A. That will be 10 divided by 2A squared. The answer will be 5 over A squared. All right. So that way I know all the dimensions, well, in terms of the width. Now let's compute the cost. So the area for the base, so it's going to be equals to the length times the width, and the answer will be 2a squared. So moreover, the area of 4 sides. So you see the dimension is going to be 2a, a, and then it will be h over here. So the area of these 2 sides are simply going to be a times h, and the area of the front and back sides, that will be 2a times h. So the area of the 4 sides summed together, that will be a times h plus a times h. So this will be the left and the right. And the front and back will simply be 2ah plus 2ah. All right, so that way we simplify this guy a little bit, so we get 6 times ah. So notice that h is going to be equals to 5 divided by a squared. So this whole thing simplifies to 30 divided by a. So this is the area of the base and the area of the sides. And using these areas, we can compute the cost. And let C be the cost. Then C is a function in terms of A, and C is going to be equals to 10 times the area of the base, namely 2a squared, plus 6 times the area of the sides. All right, so then this is going to be the function c in terms of a, and simplifying, I get 30a squared plus, well, I will just keep 6 times 30 over here, so that will simply be 6 times 30 divided by a. Okay, so this is the function we wish to optimize. Now let's determine the range of a. So clearly a has to be strictly greater than 0 because, well, if a is equals to 0, so then we have got a volume 0 that doesn't fit our choice. But moreover, is there any other conditions? Well, you could actually make the a very, very large. You could make a very, very large. So the price you have to pay is the height becomes very, very small, but then this is still allowed so that a is greater than 0 is basically the only restriction I have. So then the domain of my function is simply going to be 0 to infinity. All right, so then this is the cost in terms of the width. Now let's take the derivative. So dc over dA, so this is simply going to 30 times 2a, then plus, well, 6 times 30 as a constant in the front, then the derivative 1 over a is simply going to be minus 1 over a squared. Okay, so I can certainly factor out 30 times 2 in the front. So that will be a minus 3 divided by a squared. And I can further actually write it as a simple fraction. So that way I get 60 times a squared, a cube minus 3. All right. So you see that this derivative exists everywhere when a is greater than 0. A is greater than 0, so then this denominator is never 0, so we don't need to worry about that kind of critical number. All we need to worry about is dc over dA equals to 0. This means a cube equals to 3, so this tells me a equals to cube root of 3. All right, so this is the number, the critical number I'm looking for. And moreover, well, you could either try the first derivative test. So you look at the first derivative test, you see that if a is less than, so this is my domain and this is my critical number. If a is a little bit smaller than cube root of 3, so that you see that over here, so a cube minus 3 will be smaller than 0. So as a result, the function will be decreasing. And then after cube root of 3, the function will be increasing. Okay, so this process tells me that c of cube root of 3, and I think we need to compute it a little bit. So this is going to be close to 30 times cube root of 3 squared, so that will be 9, and then plus 6 times 30 divided by cube root of 3. Okay, so this is an ugly number, but we can make it look nicer by simply factoring out the common factor, 30 divided by cube root of 3. Okay, so then the cube root of 9 would then become cube root of 27. Cube root of 27 is simply 3. Okay, so the second term after the factorization is left with a 6 over here. So 3 plus 6 is equal to 9, and 9 times 30 will be 270. So 270 divided by cube root of 3. So this is the absolute minimum. Okay, so then notice that we are looking for this cost over here. So the answer is the cost for the cheapest such container is 270 divided by cube root of $3. Okay, so certainly in real life, well, if you tell your accountant, okay, it's 270 divided by cube root of 3, he or she will. So certainly in real life, it's not reasonable for you to show your banker that you want to pay that much money. So you need to actually tell your banker a decimal number, but because this course does not allow calculators, and so this answer will be accepted as a good answer for the final exam. All right, so that will be the solution for this problem. Certainly another way to justify that you have got an absolute minimum is just to apply the method that's similar to the closed interval method, so that you just look at the limit of C of A as A approaches 0. Okay, so this is simply means you want to compute the limit of 30A squared plus 6 times 30A. So the first guy approaches 0. The second guy approaches positive infinity. So that's basically telling me that, well, I have got infinity over here. So on the other hand, if you compute the limit at infinity, so you will see that, well, this guy becomes large and this guy becomes very small. So the answer will still be a large number. So the answer will be infinity. So then you certainly still need to compute a C of cube root of 3. And then you, after struggling for some time, you actually get a finite number. So then this will be the absolute min. So this is just a similar method as the closed interval method. All right, so then you formulate your answer. Similarly, the cost of the cheapest such container is $270 divided by $3. Okay, so that concludes the discussion of number 16. So I will conclude this supplementary video with the following problem. So the problem states as follows: a cone-shaped paper drinking cup is to be made to hold 27 centimeters cubed of water. So find the height and the radius of the cup that we use the smallest amount of paper. So here, well, the most difficult part is to how to obtain the area of the cone without the base. So that way we will get the smallest amount of paper. And that's precisely why I think this problem is a little bit too difficult for the final. Well, in the final exam, if we were to test you such a problem, we will give you the formula. But let me actually work with the formula first, and then let's actually discuss how to obtain the formula a little bit later. So let me start by introducing notations. So let R be the radius of the base of the cone, and let H be the height of the cone. So then, so here is actually the facts we should know. So, so let's say this is going to be my cone with the base, with the top open actually. So that this is my R and this is my H. Okay, so the formula we should know is the following. So the area of the cone without the top or the base actually. So this is going to be equals to, A is going to be equals to pi R times root of R squared plus H squared. Okay, so let's solve the problem using this formula. And then I will explain how to obtain this formula a little bit later. Okay, so from the fact that volume is 27, we know that 27 equals to 1/3 pi R squared H. So from this, we will be able to get H equals to 27 times 3 divided by pi R squared. And instead of writing 27 times 3 as 81, I would prefer to write it as 3 to the 4th power divided by pi R squared. Well, this is because I know, well, there will be a lot of square roots going on here, and writing this, writing in this way is probably going to be simplify the arithmetic afterwards. Okay, so then I will just use my formula. A equals to pi R times root of pi R squared plus H squared, and I will just plug in my H, resulting in a pretty horrible expression. So it will R squared plus, okay, so it will be H squared, that will be 3 to the 8th divided by pi squared R to the 4th. Okay, so, well, to get the derivative of this guy, well, it will be wise if we just multiply this R inside. So that way I don't need to invoke the product rule. So this will be pi times root of R to the 4th plus 3 to the 8th divided by pi squared R squared. Okay, so, well, now let's actually get the derivative. Let's just do this in a stupid way, because later we will see that due to the same reason, as the distance. So minimizing a is the same as minimizing a squared. So we can directly take care of this derivative inside here. But let's first do it in the stupid way. So let's just find dA over dr. So this is going to be pi as the constant in the front. Then using the chain rule, I will need to deal with 2 times root of r to the 4th plus 3 to the 8th divided by pi squared r squared. Okay, so then I need to use the chain rule to get the derivative in a function. That will be 4r cubed plus 3 to the 8th divided by pi squared. This will be the constant. And then the derivative 1 over r squared, that will be minus 2 over r cubed. All right, so this is going to be the derivative of a versus r. And as you could see from here, so when r is positive, everything in the denominator is positive. So I don't need to worry about this factor really because, well, everything simply exists and it's never 0. So all I need to worry is about this guy. So that dA over dr equals to 0. So this means 4r cubed equals to 3 to the 8th power divided times 2 divided by pi squared r cubed. So this will actually, well, imply that r to the 6th power is going to be equal to 3 to the 8th power times 2 divided by 4 pi squared. And well, I can actually simplify this guy to 3 to the 8th power divided by 2 pi squared. All right, so this is the 6th power of r. So if I take 6th power on both sides, well, what will I get? I will get r equals to 3 to the 8 divided by 6 over 2 to the 1/6 power times pi to the 2 over 6 power. And then, well, the answer for this will simply be 3 to the 4, so 4/3, and then 2 to the 1/6, and then times pi to the 1/3. Okay, so this is the critical number for the area function. So the next step is to determine if this number gives a maximum or a minimum. And for this problem, you could actually do it in both ways. So the first way is obviously to use the closed interval method. I think that this is probably easier. So because as you see that the limit of a of r as r approaches 0 from above, well, if you look at the limit of this guy over here, you will see that, well, this guy goes to 0, but this guy goes to infinity, so that will be infinity. And moreover, the limit of the area as r approaches positive infinity, well, this will simply be the limit of this guy plus this guy. Well, second guy goes to 0, but first guy becomes very large. So as a result, I know that this limit is going to infinity. Okay, so this way I know that from my closed interval method, so I won't bother to actually write down the area for this guy. But I know that this is going to be the absolute minimum. Because, well, all we need to compare is going to be the value at 0, the value at infinity, and this value over here. And certainly, alternatively, you could actually use the first derivative test. So from 0 to infinity, and then you have got one critical number. Okay, so using the first derivative, all I need to determine is what happens to this guy. If r becomes smaller, will this guy becomes less than 0 or greater than 0? And this is pretty easy to see. So because if r is getting smaller than this number, so, well, this number is precisely makes this guy 0. Okay, so but if r gets smaller, that means this guy becomes smaller. And then 2 over r cubed will become larger, but together with negative sign over here. So this minus 2 over r cubed, so this will also be smaller. So if r is smaller than this number, then this guy is smaller and this guy is smaller. So but when r equals to this number, it's going to be taking 0. But when r becomes smaller, so this will tell me that the derivative should be less than 0. So that's how I get the function to be decreasing when r is smaller than this critical number, and r will be increasing when r is larger than this critical number. Okay, so this is another way to tell the same conclusion that the area takes the absolute minimum at this number. All right, so notice that we are not looking for the area, so we don't need to bother computing what this area is. because we are just looking for the height and the radius. And now we know the radius, and all we need to get is the height. Okay, so using the fact that height equals to 3 to the 4th divided by pi r squared, and you're plugging r here. So what you will get is actually 3 to the 4th divided by pi times, okay, what's r squared? R squared will be 3 to the 8 over 3 times, so this will be dividing, but division is simply becomes multiplication afterwards. So that will be 2 to the 1/3, and then times pi to the 2/3. Okay, so simplifying this horrible expression, what you will get is the following. So 2 to the 1/3 will be kept on top, and there's nothing I can do about it. And then 3 to the 4th, that will be 3 to the 12th divided by 3. So 12 minus 8, that will be 4. So that will be 3 to the 4 over 3 on top. And then pi together with the 2 over 3 power on top, I will get pi to the 1/3. Okay, so I'm afraid that this guy cannot be further simplified. So this is precisely our answer. So our answer is, well, the radius. So let me just write this following. So if the radius equals to 3 to the 4 over 3 divided by 2 to the 1 over 6 pi to the 1 over 3, and the height equals to 2 to the 1 over 3, 3 to the 4 over 3 divided by pi to the 1 over 3. So then, well, the cup uses the smallest amount of paper. Okay, a few remarks over here. So the first remark is to optimize. A for this problem is the same as optimizing is to optimize a square. So, well, this can also be seen from here because we are optimizing A, and we find that the most important thing is really the inner function, the derivative of the inner function. Well, but if you directly start from A square, well, A square is precisely going to be the kind of like the inner function, namely pi squared times r to the 4th plus 3 to the 8th divided by pi squared r squared. Okay, so yeah, you could directly start from this guy over here and take the derivative, and you will directly come to the same equation as well. So, so if you notice this fact, then you don't need to bother with this annoying factor in the front. So this is the first remark that can help to simplify the computation. Okay, the second remark will be about this formula. So how do I see this formula? And let me actually explain it here. And this is definitely not going to be required in this class. So if you're already feeling tired and you don't want to continue, certainly feel free to stop. But just if you're interested, then please continue focus on me. Okay, so I will just need this picture over here to explain what's going on. So you know that such a cone is obtained by folding a sector like this. So we simply identify the CA and CB, and that way you get such a paper cup. So with this in mind, you could easily see that if I want the area of the paper materials, so the area is precisely the area of this sector over here. Okay, so this means we need to figure out the relationship between this sector and the cone. And here's a key observation, that the arc from A to B, so this arc is supposed to be the same as the circumference of the base of the cone. So this is basically telling me that if I have got a theta to be the angle of this, if theta is the angle of this sector, then what we should have is theta times r. So this is going to be the length of the arc AB, and this is supposed to be equals to 2 pi times lower r. Okay, so this is the relationship between the theta and the lower r. But now we are looking for the area. So then the area of the sector, area of the cone without base, So this is going to be the same as area of the sector. And well, area of the sector is simply going to be theta divided by 2 pi times pi r squared, because, well, this is precisely the ratio of this sector compared to the whole disk. And then the area of the whole disk is, oh, okay, so I made it wrong here. This should be capital R squared. Should be theta over 2 pi times capital R squared. So then the area of the whole disk is going to be this guy, and the area of this sector will simply be obtained this way. Okay, but now we know my theta. My theta is obtained in this way, so that I know my area of the sector is going to be 2 pi r divided by capital R. So because this is seen from here, that theta equals to 2 pi r divided by capital R. So I substitute this theta out. So then together with the rest of the terms, all right, so this way I get the following. So this 2 pi is gone, and one copy of capital R is gone, and what remains is simply going to be pi times R times capital R. All right, so but what's my capital R over here? Remember in this picture, so in this cone picture over here, so this radius is the same as R over here. So that's what my capital R is. So from here, I get the capital R equals to square root of lower r squared plus h squared. All right, so that's how I get my formula. So pi r times square root of r squared plus h squared. Okay, so this fills the gaps of the previous problem. So this is how I get my area in the previous problem. Okay, so this concludes the supplementary video. So I think the number 42 is definitely way too difficult than an actual exam problem. So if you feel like this is way too difficult, it's fine. Don't worry too much about it.